Hello, this is a redo of Probability Statistics Revision Seminar, Semester 1 2016, and I had specific requests to talk about Markov chains, discrete time Markov chains, and in particular what to do with the absorbing states and the way the matrix gets rearranged when you do that. So, Markov chains with absorbing states. Okay. So just to get started on that, I'll draw a picture of Markov chain and the way I've envisaged it. When I think about Markov chains, I think about them as little ant farms that have little regions where the ants live that have paths between them, and then every time the time moves on by one's time period, the ants all choose a path to walk out from and end up in one of the other corners, and then you do it again, and then you do it again, and then you do it again. And what the probabilities describe is how likely it is for an ant to move from one place to another, and you imagine sticking 10,000 ants in there and watching where they go, basically. So I'm going to do one with 5 states. So these are little places where the ants can live, and maybe from state 1 it's going to go half the time your ant's going to walk around and back into state 1, and half the time it's going to walk across and end up in state 2, and maybe state 2, the only out path goes back into state 2. And these numbers here that I'm writing are probabilities of how likely it is for an ant to end up going down that road. And maybe state 3 goes to all the other states and not to itself. I'm just making one up here. Maybe state 4 does the same as what state 2 does. And state 5, let's say, it goes to itself like that, and over to 1.3 and down to 0.6. Okay. So that's my picture of a Markov chain. And I just need to check if it's a valid Markov chain, then all the arrows coming out of a particular number will add up to 1. 1, 2, 3, 4, yeah. Which they do, and that's a picture of a Markov chain. And I literally do imagine it as pouring 100, well, or 100,000 or whatever ants into it, and watching where they go. And so if I stuck 100 ants in here, 50 of them would walk around here and end up back here, and 50 of them would end up over at state number 2. And then I did it again, and then 25 of those ants would end up back in state 1. 25 of them walk across to state 2, but all the ones that were already in state 2 would end up back in state 2, so we'd end up with 25 here and 75 here. And that would continue like that. Whereas if I put them over here in state 3, I'd get 10 here and 20 here and 30 here and 40 here, and the 30 that end up here, 60% of them will end up down here. And so eventually the ants will settle down somewhere if you wait long enough. To be fair, an ant could be sitting there in state 1 and go round and round in state 1 forever, but it's less and less likely the longer you leave it. So if you sort of wait forever, the ants will tend to collect in the corners where they can't get out. So if you're in state, circle 4 or circle 2, the ants are going to only be able to stay there. And so ants are going to come into state 2, but they're never going to leave. And so state 2 and state 4 are going to eventually end up with lots of ants in them, and there'll be nothing left in 1 and 3 and 5. That's the idea of how I imagine Markov chains. Of course, it's not really ants, it's often, weather or the state of your computer system, whether it's running or not, or any number of things. It could also be about infection, how many people are infected or about to be infected or have gotten better, all of these sorts of things. So the key to this particular example is it has absorbing states. These ones that have ones on them, it's impossible to get out of them, and so they are called absorbing states. So it's impossible to get out of 2 or 4 because 100% of the ants that live in 2 will end up back at 2 again. So they have probabilities of 1, and they're called absorbing states. And so this is specifically about absorbing states. In your lecture notes, there's other different possibilities of different kinds of Markov chains. Some of them don't have absorbing states, and they've got their own possibilities for how you deal with them. Okay, so with any Markov chain, whether it's got absorbing states or not, you can represent all these probabilities in a matrix. So each state has a column and a row, like that. And in some courses or some places in the world, you'll put a column vector here to represent what probability it is, the starting probabilities of being in any one of these things. So if I equally spread them and put 20 here, 20 here, 20 here, 20 here, 20 here, I would have a starting list of probabilities, and that starting list of probabilities is a vector. And so what I'm going to do, in some places you can put that as a column vector, and in some places you put it as a row vector, and in this course it's a row vector. And so being a row vector, it has to go on the left. Sorry? Yeah. So that will change the structure of your matrix because of what's supposed to happen there. So if you stick a row vector here that represents the probabilities of currently the case, what's supposed to happen is if you had 20 in each of them, you could figure out the probabilities, how many of them would end up in each of the other spots. So if I had 20 in each of them, for example, if I had 20 in all of them, afterwards my number 1 would still have 10 from itself. It would gain 6 from number 5, and it would gain 4 from this one, and so it's going to still have 20 afterwards. Whereas the number 2 will still have 20, and it's going to gain 2 from 3 and 10 from 1, so it's going to end up with 32. And so you can figure out the probabilities that go with that. This would start as a 0.2 and it would end as a whatever. And so that's what's going to happen. When you multiply this row vector here by the matrix, it will turn out to be the distribution of your ants afterwards. And the nice thing about it is that if you put 100% of your ants in one of the positions, if I put 100% of the ants here, my vector will be like 1 for 100% and 0 for all the others. And when I multiply that by this matrix, it's supposed to produce what the next distribution is. And so after that, I should end up with 50% here and 50% here and 0 in all the others. So each row is going to be a description of what those arrows are, basically. So row number 1 will describe what happens to the probabilities for row number 1. So if I start in row number 1, I'm going to have a 50% chance of ending in row number 1. Let me zoom out a bit so that you can see all of this at once. It doesn't go out any further than that. Really? Half as half. It goes in, obviously. Wow. This is a very high power. Come on. That's as far out as it goes. Okay. So number 1 has 50% end up back in number 1. And 50% ends up in number 2, and none ends up in the others. So that row number 1 is a description of what happens. It's the probability of ending in each state when I start in row number 1. So starting state 1, probability of ending in each state. Okay, so the next one, state 2, well, you don't end up in state 1 if you start from state 2. You always end up in state 2 if you start from state 2, and so that'll be like that. State 3, 0.1 ends up in state 2, 0.2 ends up in state 1, 0.3 ends up in state 5, and 0.4 ends up in state 4, and it's impossible to end up back in state 3. State 4 is 100% goes into state 4, and state 5 was 0.1 back into state 5, 0.6 into state 4, and 0.3 into state 1. Okay, so that's my matrix. That's your traditional transition matrix, I believe it's called. Is that right?
Yep.
And I can check it by putting 100% of my ants in any one of the columns and any one of the spots and multiplying it. Okay, but the thing is, this transition matrix, which your lecturer likes to call Blackboard bold P, because it's full of probabilities, that transition matrix is great, and if I want to figure out what the probability of getting from any one state to any other state in one step, I can do that. If I wanted to figure out how the probability of getting from any one state to any other state in 2 steps, I'd do P squared, because I do P and that's the first step, and then I do P again and that's the next step. And so I can figure out the probability of getting from any one state to any other state. And if I sort of did this process forever, I would just like P to the power of infinity, so the limit of P to the power of n. Now most matrices sort of wrap around in some sense. They go around in circles when you do powers because of the Cayley-Hamilton theorem. So the Cayley-Hamilton theorem says that any power of a matrix says that there is a polynomial of any matrix that it satisfies. It comes out to the 0 matrix, which means therefore that any power of a matrix can be written as in terms of the first few. So high powers of a matrix are just linear combinations of low powers of a matrix, and therefore I can expect it to have a limit as P to the n goes to infinity, especially because all the rows add up to 1, which means that we've actually got an eigenvector, and so there are some vectors that aren't changed by this matrix. So, however, the fact that there are absorbing states means that this matrix has some very useful structure, and it might be better to draw my columns and rows in a different order. So that row number 2 there, I'll just circle it in a different colour. Row number 2 there, because it's an absorbing state, this is a row of the identity matrix. And because because state 4 is an absorbing state, that is a row of the identity matrix. And so if I arranged it so that those 2 rows are at the bottom, we'd get some convenient zeros. And if I arranged it so that the columns that went with those were at the end, I'd actually end up with an identity matrix in the bottom right-hand corner. And that would give me a block matrix, a block triangular matrix, and they have certain properties with their matrix multiplication. So I would rearrange that, the columns and the rows. And what I'll need to do is I'll need to want to rearrange those columns and rows, and I'll need to make sure that the rows are in the same order as the columns, but not the same order they were before. So what I'll do is I'll put the non-absorbing states first and then the absorbing states last. So my absorbing states were 2 and 4, and then I'll have 1, 3, 5. It's a coincidence that my absorbing states were the even ones. That's not always true. And then I'll put them in the same order here. So you could, if you wanted to, take this matrix and literally rearrange the rows and the columns. I find that harder than just going back to my diagram or reading off from this matrix what goes where. So here I am in state 1, and state 1 it goes 50% to state 1, and 50% to state 2, and 0 for the others. So basically just rearrange each row. State 3 is 0.2 for state 1, 0.1 for state 2, 0 for state 3. Let's see if I can fit them both on the same screen. So it's working my way along. So it's for state 1 it's 0.1, for state 3 it's 0, for state 5 it's 0.3, for state 2 that's 0.1, and for state 4 it's 0.4. And you can read it off the other matrix. For state 4, sorry, I'm not up to state 4, I'm up to state 5. So for state 5, it's 0.3 for state 1, state 3 would be 0, state 5 would be 0.1, state 2 would be 0, state 4 would be 0.6. And now I'm up to the absorbing states. State 2 is an absorbing state, it only ends up back in state 2, and state 4 is an absorbing state, it only ends up back in state 4. And the nice thing about this is that if I do this, I've got an identity matrix here and a zero matrix here. Your lecturer calls this matrix here S and this matrix here R, for no good reason. They're just letters that come after P. So just to make that absolutely clear, like that, which means that my transition matrix has now become R, S, zero matrix, identity matrix, like that. A useful thing to keep track of when you do this is to remind yourself which columns belong to which things. So 1, 3, 5, and 2, 4, and this was 1, 3, 5, and 2, 4. Just to keep reminding myself that the states are in a different order than they were to begin with. They're not in the order that's defined by the numbers that they have. Okay. So there's this thing in the notes which says that if your matrix is in block diagonal form like this, then you can shortcut the process of multiplying and not do all of it at once. And so you don't actually have to multiply P by itself, because you can just have to multiply P by its various different, each part of P by the other parts of P. So we can now say that P to the n is R to the n 0 I and I plus R squared plus R to the n minus 1 S. Like that. I believe that's correct. Just let me look that up. So I'll just go to the built-in computer. There we go. That's right, R to the n, and the sum from I equals 0 to n minus 1 of R to the I S. Good, I was right. And actually, if you do the limit as n goes to infinity, you'll end up with 0 here. And, whoops, sorry, docking the camera. You'll end up with a 0 in that spot just there. The R to the n will go to the 0 matrix, and that's because it has 0 as one of its eigenvectors, 0 eigenvalues automatically, the R. And the 1 plus R squared plus whatever, if they were numbers, that would be 1 minus R to the n over 1 minus R, if they were numbers. And it works perfectly well for matrices, only there's no such thing as 1 minus R. That would be I minus R inverse. We'll get that. So the number theory sort of thing that goes with that is that 1 plus R to the n minus 1 is equal to 1 minus R to the n over 1 minus R. And the limit as R goes to n goes to infinity of that, if R is less than 1, that will do this. And if they're matrices, well, you know, it also works, basically. So with matrices, the limit as n goes to infinity of 1 plus r plus the n plus minus 1 will be 1 minus r to the minus 1. So that's sort of the matrix equivalent of this. There are rules as to what R has to do as a matrix in order to do that. I'm pretty sure that you need all of the eigenvalues of R to be less than 1. Yeah. Okay. Just so, because I couldn't necessarily remember this, but if I can remember that one, I can abstract this one if I remember pieces of it. So, yeah. Okay. Just as an aside. Okay. So the question is, how are we going to use that? So I'm just going to do a couple of examples of using that. So e.g. probability of going state 3 to state, say, not state 3, just a second. Yep, it's from state 3 to state 5, say, in 2 steps. Okay, that's what I'm going to figure out, which means that that's the entry in the row labelled 3 and the position labelled 5 of p squared. It's not row 3, it's just whichever row is called 3. It's not column 5, it's whichever row is called 5. It's named after the state. And then the number of steps is the p squared. Okay, so we know that p squared is r squared I plus r s 0I. And just to remind ourselves, we had 1, 3, 5 and 2, 4 here, and 1, 3, 5 and 2, 4 here. So if I want row 3, if I want row labelled 3 and column labelled 5, that will be part of the r squared. So essentially I don't need to figure out what any of the other stuff is, I just need the r squared. Okay, so r squared 0.5, 0.2, 0.3, 0, 0, 0, 0, 0.3, 0.1. And I'll multiply that out and see what I get. I mean, technically I don't even need to do the whole matrix, I just have to figure out the exact one that I want. So I could start calculating that, right? So I could do 0.5 times 0.5 is 0.25, 0, 0, 0.5, 0.5 times 0. Okay, so that row was easy. And then 0.2 times 0.5 is 0.1, and that's 0. And 0.3 times 0.3 is 0.09, so 0.19. But I don't actually need to do all of those, but I'm just going to do them all anyway. 0.5 times 0.3 is 0.15, 0, and 0.03 again. 0.18, 0, 0, 0, and 0.01. Okay, so I could do all of that. Technically the only one I actually need is because this is one labelled by 135 and 135. I want row 3 and position 5, which is this one here. So technically I don't need to do the whole matrix, all I need to do is figure out that one. which would have actually come from row 3 of this, row label 3 of this, and column label 5 of this. That would have given me that position. So I could have just done that, and it would have produced that number there, and I wouldn't have had to do any of the rest of it because that's the only one I want. So probability that I'm looking for is 0.03. Okay. Another example with this one, just to round this off. Is the probability of getting state 5 to state 4 in the long term. So we know that state 5, we know that eventually, if we do it forever, you'll either be in state 2 or state 4 because they're absorbing states. And so I can sort of completely, so I know it has to be in one of them, so I want to figure out probably be in state 4. So I would do, that would be the entry in row 5, position 4 of the limit as n goes to infinity of p to the n. Okay, so limit as n goes to infinity of p to the n is the long-term transition matrix, and I want it in row 5 and position inverted commas 4, and that limit is 0 I minus r inverse s 0 I. Okay, so let's just see, this was 1, 3, 5, this was 2, 4, this was 1, 3, 5, and this was 2, 4. So the position I'm looking for is row 5, position 4, which is part of this matrix here. So I'm going to need to figure out what I minus r for the inverse S is, because I want row 5, position 4, which is part of that matrix. Okay, so I'm going to need to calculate what I minus R inverse S is. So I could calculate what I minus R inverse is, and then multiply the appropriate row of that with the appropriate column of S to get what I want. Alternatively, I could directly calculate what I minus R inverse S is without having to do matrix multiplication, which is a really clever trick, and you should know all about it. That's a great trick. So I minus R, let's just calculate what that is. So let's see, where's my R? There's R there. So I minus R. So all the other bits will be minus what they are, other than the ones on the diagonal. And then the ones on the diagonal will be 1 minus that. So 1 minus 0.5 is 0.5, 1 minus 0 is 1, 1 minus 0.1 is 0.9. So that's my I minus R. And the I minus R inverse times S, well, here's the really clever trick. If I wanted to calculate I minus R inverse, if I didn't have a computer handy, I would need to do row operations. That'd be the quickest way. I could do adjugates, I suppose. That would totally work, because I only actually need one of the rows of this matrix. So I could use the adjoint if I wanted. That would be kind of cool, but I'm not going to do that. I could do it with row operations, and I could have put an identity matrix here and do row operations until, I could put an identity matrix here and do row operations until this became the identity, and at that point this would be the inverse. But when you do that process of sticking the identity matrix next to the thing, what you're actually doing is multiplying I minus R inverse by this matrix here. So I can put any matrix there, and if I do row operations to make this into the identity, by the time I get from here to here, this will be whatever that matrix is times the inverse on the left. And that's because of elementary matrices from this 1A. So I can actually just put the matrix S here. Actually, we'll start on a new page because I'm going to need space. So I minus R S 0, 0, minus 0, 2, 1, 0, 3, 0, 0, 9, and S was S was 0.5, 0, 0.1, 0.4, 0, 0.6. So all I need to do is do my row operations. And I can be a bit sloppy about it because that's not the important thing. Not sloppy in terms of getting the answer wrong, but sloppy in terms of doing the things I need. If I multiply this top root by 2 or divide it by 0.5, I'm going to get 1, 0, 0, 1, 0, and that will be my first row of the identity matrix. And this bottom row, everything's a multiple of 0.3, so I'm going to divide by 0.3. Give me that. And now I have the correct first row of the identity matrix. I have the correct middle column of the identity matrix. Normally you work one column at a time, and so I'll create zeros here. So if I add this row onto that row, I'll get 0, 0, 3, 1, 2. And then if I add 0.2 of this row onto that row, I'll get 0, 1, minus 0.3. So that'll be 0.3 and 0.4. Almost there. The only other thing to do now is to create a 0 here and a 1 here. Don't seem to have a page for that. And so I suppose if I times this one by 0.1, I'd be able to make everything match. So I know that's probably not the most efficient method, but I'm going to do it anyway. So now if I add those two rows, didn't change my last row. Add this onto there, that'll be a 0.4 and a 0.6. Pretty sure? Yep. And then my final thing will be to divide that one by 0.3, which is the same as just dividing this one back here by 3. And there we have it. So by the time we get to this one, this matrix here is I minus R inverse times S, because this matrix here was I minus R, and this matrix here was S. So when I do row operations like this, by the time I get to the bottom, it'll be the inverse of the left-hand one on the left-hand side of the right-hand one. And so the entry I'm looking for is the entry that goes with, I might just write that matrix again on a new piece of paper. So I minus R inverse S. Now let's just see S. This matrix over the corner here was the columns were 2, 4 and the rows were 1, 3, 5. I wanted to know getting from state 5 to state 4. So that will be this one here. Row for 5 and position 4. So the long-term prob from state 5 to 4 is 2/3, because that's the position I'm looking for. I can tell the long-term probability from state 1 to state 4 is 0, the long-term probability from state 3 to state 2 is 0.4, and so on. And without even calculating, I know what the long-term probability of getting from state 5 to state 3 is. It's 0, because you'll always end up in an absorbing state. So, just to point that out, probability from state 5 to state 3, say. Well, state 3 isn't an absorbing state, so you can't end up there at the end. And you can even do that. This will be the entry in row 5, position 3, and row 5, position 3, of the limit as n goes to infinity of p to the n, which is 0, 0, I minus r to the minus 1 s I. Well, look at that. This was 1, 3, 5, 2, 4. This was 1, 3, 5, 2, 4. So to get from state 5 to state 3, that's part of a zero matrix. So the probability is 0, the one that I'm looking for. But you can tell that even without looking at the matrix, because it's not an absorbing state. So state 3 isn't absorbing. Now that statement of it not being absorbing, so the probability is 0, only counts for matrices that have absorbing states. Isn't absorbing and other states are. If there aren't any absorbing states, then you do have a chance of ending up in state 3 long term. Sorry.
Because all the arrows are just going away from state.
Well, not that state 3, but in a general one. If you have a non-absorbing state, it might be possible to find ants there. Yeah, but you're right. State 3 in general only has things going away from it, so you can't end up there. But that's worthy of note as well. So if you do just have something, if it didn't have absorbing states, and one of the states only had arrows pointing out of it, then it would be impossible to end up there. And that's actually true. If you have a matrix with a column of zeros, every power of it will have a column of zeros there as well. So, yeah, good point. I like it. That's enough of that one. I was not going to talk about the rest of the Markov chains. I specifically asked about that, so that's what I'm going to do.